channel between you. But also you can ask some of those questions. I guess that almost most of them are applicable to the panel discussion, and you can ask. And now we have the panel discussion. So Carlo, you are the moderator, and you can take the floor. Carlo, can you hear me?
Yes.
Okay.
So good afternoon, everybody, and now it's time to move here to our panel discussion here. Hussein and Mayrton have put together a distinguished panel of speakers, and in particular we have Denis Kudus. We have already heard from him in the morning. Then we have Walid Saad from Virginia Tech. We have then Petar Popovsky from Aalborg University, and Hamed Farhadi from Ericsson Research. And I don't know if our panelists are already here, connected. I can see Denis and...
Yeah, Denis as Hamed are here, but I cannot see Petar and Walid.
Walid is here.
Yeah, I can see Walid as well. So Petar, if you are in the attendees, maybe you can raise your hand so I can see your account. Yeah, I see. Promote. So Petar, you are user 1234 or not? No, he wasn't. Maybe you can start, and then whenever Petar joins, he will join you.
Okay, let's do like that. And finally, my name is Carlo Fischione. I'm a professor in the Division of Networks and Systems Engineering in KDH, and I'm supporting Mayrton and Hussein and Mayrton in the organization of this course and workshop today. I would like to start now with a simple question just to warm up ourselves. Then I will go through a little bit more technical or technological questions, and then we will have also opportunity to get the questions from the audience. So the audience that I see very numerous, please already start to prepare questions that you would like to ask, and especially questions that should be of a higher, so to say, abstraction level. I would like to ask first that to every panelist, if you have any personal somehow reason or feelings why you started to work with machine learning. Is that any episode that has happened in your research or in your technological readings that motivated to work in this area?
Shall we go just random order, or how do we do it?
Yes, the first who wants to exactly to answer is welcome.
Okay, I mean, I can start since I'm the first in those photos. Okay, so maybe I should actually also share start the video.
Dennis, you
Yes.
sent me some introductory slides, and if you want, you can go through them.
So
just if you
okay,
want
so
to.
I mean, I shared some slides because I mean, yeah, you asked these 3 slides. To be honest, I didn't know what to include them. So since I already gave the talk as well, I mean, they're not needed. So let's say, I mean, let me answer this. Let's continue, and then somehow there is the need to use the slides. Then I can refer to those. So, but to answer this question, kind of how it started. I mean, in my case, I can luckily say that, it's not because of the, kind of just because now it's popular, everybody is doing it and then I'm also doing it. I mean, it could be the case, that's fine, you know, in many kind of cases, of course, you kind of, I mean, there are certain reasons, of course, why certain topics are popular, and then you might just kind of get interested in that because of the kind of the, let's say, social pressure. So in my case, luckily, actually, I started a bit earlier. And to be honest, like the main reason was that, so my PhD was on information theory. And at some point I was a little bit bored of, you know, doing kind of similar things. And actually, I mean, reinforcement learning, because it was kind of this Markov decision process background of, you know, reinforcement learning seemed something actually that's aligned, let's say, with my information theory statistical background, and it was something different. It wasn't as popular as it was at that, I mean, it was like 2010, 11, so I was at CTTC in Spain, so there were some people who were doing these things, you know, like even much earlier. So that's how it started. But then I was a bit lucky that when I joined Imperial, as opposed to kind of the normal expectation that instead of joining the communications and signal processing group within the electrical engineering department, for completely practical reasons, I joined the intelligence systems and networks group, which is basically the group that does the machine learning. And that's how I kind of started talking to people, learned about, you know, neural networks, you know, etc., and then, you know, started collaborating. So yeah, that's how it started.
I remember in the year 2013, 12, that people started to somehow to speak about, and my perception from the opinion of many people is that they were very skeptical about this. But then we have seen that actually there is a need, is a technological need, and this has for sure reinforced the interest now in the community to work in this exciting area. But yes, it's interesting that things started in a way that many people perhaps discount ideas and then they convert again in the future. Very good. Walid, do you want to?
Yeah, I could go next. So thank you for inviting me to this panel. So I started in learning. It was really part of my PhD. So I finished my PhD in 2010, but we can say we started around 2008 because my PhD was really focused on multi-agent games, and the game theory is, I mean, reinforcement learning and learning in general comes, hand to hand with game theory. So at that time, we used to use it a lot to basically characterize the equilibrium of a game in wireless, right? So you have, let's say, simple power control to more elaborate cases. So we just, I mean, it really continued as a flow. So it was not really a major change of the work that we've been doing. It's just like, we had more neural networks over the time, maybe back in 2000, early on in deep learning. We used it a little bit also. In my PhD, we looked a little bit also at this type of classification for security, basically in the days of cognitive radio. So we used some sort of unsupervised learning, so Bayesian non-parametrics at that time, to basically characterize the transmission pattern of primary users. So there were these two big threads which we've been working on, and it just kind of continued with, of course, the new things that started to appear, which were like basically add-ons on that.
There was a natural transition in a sense from your research.
Yeah, it was not, I mean, maybe we rebranded from ML to AI, but it's basically the same.
And very good. It's Hamed, do you want to add if he's online?
Hello, everyone.
Hello.
Thank you, Carlo, for giving this opportunity to be part of this panel. My name is Hamed Farad, and I'm a senior researcher at Ericsson Research. I'm working on AI technology for 5G and future 6G standards. So, well, I would say that my first exposure to this AI domain was a long time ago. Maybe back to 15 years ago, when I was trying to implement neural networks at that time on FPGA when I was undergraduate students. it was a very challenging task at that time, but now due to the vast developments that we have seen in the computational domain and also in the algorithmic domains, these kind of algorithms are very much reachable everywhere. And nowadays we are trying to enable platforms that these type of algorithms could be available everywhere, using this wireless network as a platform for learning and learning models and distributions of the knowledge through the networks. And this is a very exciting time to be. And so
excellent. And you now you're working on these topics from Ericsson. So Ahmed now is the so to say in the panel the industrial research representative.
Yeah, if there is a time, I may share a slide somehow.
Yes. That's what. Yes, please.
Okay, let's see. Could you see the slides now?
Yes.
Okay, so I would try to briefly go through how we see AI could potentially have impact on future 5G and 6G networks and systems. I think many of the topics that has been covered in today's workshop and the invited speakers was very insightful and also are part of this journey. And okay, so yeah, artificial intelligence, as I mentioned, is expected to have an important role in the vision of having intelligent, sustainable, and connected world in coming future. So it is expected that massive number of intelligent machines to be connected to the networks. And these intelligent machines that come from very wide area of applications, including intelligent transportation, medical healthcare system, smart grids, and many more vertical applications would require to train models based on the data which may not be locally available. So it is expected that these machines try to connect to the networks to both have access to massive amount of data for training and also to the computational resources that are available in the clusters and clouds. And also the machines may need to interact with the other machines or humans to have kind of supervisions for the training of the models. In this journey, actually, we would expect the machines, depending on their computational capability, and also other factors like privacy constraints and considerations, try to train the models over the cloud or over the edge or do it locally in the device. And due to this, actually, we expect that in the short term, we have kind of a huge amount of data uploading to the networks to be processed centrally in the cloud systems. And over the time, we expect that as the hardware mature and the computational becomes less and less expensive at the device side, the devices try to train their model locally, and we have the networks only for coordinations of these trainings and the transfer of the models among different machines and different domains. And we in this industry side also see that there is a rapid development in the chipset AI-friendly chipsets, the chips that are dedicated for AI processing, and this would reduce the cost of the AI processing and would be a factor that makes these technologies to be available everywhere. Another domain that is very exciting and interesting from the wireless communication perspective is the development that we see in the smart material domain. So the development in the smart materials enables to have some kind of control over the propagation environments. This is something new that we traditionally we haven't seen in the communication domain. In the conventional communication system, we have been focusing on the designing of the transmitters and optimizing the transmitters and also the receivers for given propagation environments. But now, thanks to these materials that could be controlled and adjusted by AIs, there is potential to manipulate and adjust the propagation environment so that improve the quality of communication. In another domain also, we see kind of new ways of interactions with the environments, thanks to technologies like virtual reality and augmented reality, that would require kind of models to be trained at the edge or at the devices, so that enable low delay communication while we maintain minimal traffic to be transferred to the networks.
Ahmed, I wanted to. I have many questions that I would like to ask for every one of these boxes, and then I suggest that I keep these questions for that are a little bit more technical for later on.
Yeah, sure.
And then if you can, you could conclude your quick introduction, and then we could move.
Sure, I just wrap it up, and then we can wait for the questions as well. We also see the huge opportunities to developing AI-assisted air interference algorithms that could substantially improve the existing physical layer algorithms that we have for handling the communications over the networks. And by this, I would be willing to hand over the control to Carlo.
Thank you very much, Ahmed. Then I suggest that we have Peter, who has also just joined.
Sorry, hello. There was a glitch in the connection, but I joined already before Dennis started, so I have followed all the introductions.
Okay, very good. And I wanted to start first with a general question on somehow what was the personal reasons to start working in this domain of machine learning and wireless, and before going a little bit into more the technical discussions.
So I have a couple of slides. I can just say that I'm not really, I'm not really still working on machine learning in the same way that I have never worked in statistics. But it's what I'm trying to do is I'm trying to make sense of what type of problems we want to solve and where it makes sense to use some tools which have been developed for machine learning, which are data intensive. So maybe I can share some slides which I have. Is okay?
Absolutely. Yes, please. You should be able to share. Yes.
So as I said, is for me, I mean, I don't have, I've never produced a result in machine learning, which it's also similar to the case that I've never produced a result which is significant in statistics, but I'm trying to understand what is the interplay between communication and machine learning. So I'll be fast here. So normally we are looking into the issue of algorithm deficit and model deficit and in certain problems. We are looking into the problems and hypotheses we want to address, and we are looking whether we can use traditional model-based approach or traditional algorithms specified by certain mechanism, proof, and so on. And then we can use machine learning to address problems which are not inherent to the networking capability. What I mean here is, for example, I will illustrate two problems, but I have actually segmented the problem space into three parts. First is problems that are not inherent to the network capability, but are related to communications and machine learning. Second are opportunities arising from the network capability. And third one are constraints arising from the network capability. So I'll go through this now. And this is the way I understand how the problem space is segmented for communication and machine learning. So in the first case, when, for example, there are transmission schemes, like designing of a modulation scheme, designing of a, I don't know, resource allocation thing, which is difficult to do without machine learning because of the complexity. So we apply machine learning to search certain larger space. Then I started more seriously to look into the machine learning tools like 2 years ago, when I realized that we have talked a lot about ultra reliability in 5G, but ultra reliability was always based on some models. And actually you cannot offer ultra reliable communication if you don't understand the statistics of the environment where you work. And this is naturally giving the setup of statistical machine learning that needs to be used in order to guarantee certain levels of reliability. Another practical problem that we have started to work on was that a company approached us to say, we have this IoT traffic, the devices are sending quasi-periodically. We don't know whether the device is off or it's just it has a period which is unusually large. And this was not possible to address by usual statistical model. There was some model and there was some algorithm deficit. So we have actually approached that using machine learning. So let me just briefly mention this. In transmission schemes, for example, we made this work where we looked deep learning and applied it to synchronization and channel estimation in NB-IoT. So basically the problem doesn't exist because of machine learning. We have just addressed it using this machine learning tool. In the network troubleshooting, we have made this work where we had a lot of data from
I've lost the voice from Peter. We have a little technical problem. We cannot hear Peter. Let's see if we can resolve quickly. Not, no, it's...
Can you hear me?
Yes, now we can hear you.
Yes, okay. So it comes, as I said, exactly when I speak about ultra reliability, the connection failed, which is, it's a sign. So what I'm trying to say is that you cannot guarantee high reliability without having data. So to offer high reliability, we need to have model selection, learning procedure, and then performance evaluation, which is based on statistical machine learning. I'm trying to say that offering high reliability without data-driven methods and machine learning is impossible, simply. Because you cannot guarantee 10 to the minus 5 reliability without having tested an environment where the system should operate. It's a statistically paradoxical setup if we don't use data-driven methods. And then finally, I mentioned the two other places of the problem space. I think there are opportunities arising from the network capability. And here I'm thinking, for example, the distributed computation, which is helping to solve certain complex algorithms by delegating it to the interconnected nodes. There's also the interesting approach of meta-learning, where we can have networked what's called entities, which are exchanging some of the features and some of the data related to their models, where they're basically training. And through this meta-learning process, they're trying to help each other in a certain network setup. And but there are also constraints arising from the network capability. And they also gave rise to new problems. So one is, for example, the privacy problem of federated learning, where a lot of people in the communication area work because, you know, there's a communication cost and there is also privacy constraint. So how do we solve this problem? So I see this is a opportunity in the network setup to share data, but still you have to protect it based on some privacy requirements. But I personally think one of the absolutely most interesting aspects is the cost of data and the data markets, because we will need more data to train. The question is, who has access to this data? What is the value of the data before training? What is the value of the data after training? So you might be paying for getting a lot of data, but then you don't know whether this data is going to help you in your learning and prediction. And actually, there are some interesting work starting in that area. So with this, I will conclude my brief introduction.
Thank you, Peter. I think that also this somehow shows that your research trajectory is somehow encountering naturally machine learning problems, and then this is triggering your curiosity to work in this domain. And at this point, I wanted to start the discussion here with again this sort of warming up question, but then we have Ahmed and Peter who have given a very interesting technical slides, also with some technical point. Then I would like to also give to Denise and Walid the opportunity if they would like to show their slides.
Sure, I can go ahead. Just
please,
give me a second.
please, Walid.
Yes, just a second. I have I prepared like 4 slides, somewhat aligned with Petar, but without the nice matrix. Let me just quickly make this work. Do they appear?
Yes.
Okay. So I wanted to think a little bit also, what are the use cases of machine learning? So basically in 5G and beyond, but let's say wireless in general, right? So first, I mean, the first question I would ask is why, right? Why we would need machine learning from that? And I mean, I asked this question particularly because in the past when we used to work on it, and Carlo, you mentioned that early on, it wasn't very popular. So people were always skeptical. So the question is really why we want it. So one quick answer is basically relates to the last part of Petar's basically matrix, which is that machine learning and AI will be part of wireless networks, even if it's not used for communication. For example, car or autonomous vehicles will use it for their navigation. And at that point, there will be an intersection between machine learning and wireless. So there will be an interaction between them. And the second aspect is we're clearly heading towards less rigid protocols. And this has been seen going from, let's say, the early on cellular systems all the way to 5G and beyond. So the system should be able to operate itself by itself. And what I mean by that is not just at the network management side, but also on the radio, right? So in terms of radio resource management, in terms of basically even modulation, adaptive modulation encoding, and so on and so forth. And there's this, of course, I put the third bullet, it's probably the first one that comes to mind, is basically the prediction side, right? So caching appeared a few years back, and it was probably one of the first ideas where machine learning is very clear, database machine learning. So from there, you can think beyond that, of course. So based on this, I would identify 3 roles for machine learning in wireless. The first one is, as I mentioned, this data analytics. And I would say that's already there. Caching is a good example for that. So it's not really very far-fetched. So you are collecting some data from the users, and under some privacy constraints, the operators could be able to use them for something useful. The second use case is more this basically self-organizing or AI-driven optimization and control. And that is where things come between, I mean, there's an intersection between optimization and machine learning. And the third is essentially this edge learning, which federated learning is, of course, a part of it. So, I mean, just elaborating on the 3 use cases in my next slides. So first, yes, in terms of data analytics, when we talk about an application like a smart city with all the IoT environment there, you would have like a data hurricane that wireless networks have to, if not manage, at least use, right? So how can we make sense or make use of this data from various sensors or even from the devices of the users, with, of course, the advent of applications like virtual reality. Even the user himself, like how does he move? How does he turn his head becomes important data for wireless design, right? Because if you think about the quality of experience in a VR setting, you would need that data. And I think this use case one is probably pretty much everybody likes it and everybody knows it's really probably the first entry point in terms of ML for wireless. The second one is more the one where perhaps I work more on than the first one, is where you would have tough optimization problems. They could be difficult because of unknown information, like you don't know, for example, activation of devices. You don't know certain evolution of the wireless channel. So there are some uncertainty which you cannot have. And if you formulate an optimization problem with some uncertainty, to solve it, you have two options. Either you assume some distribution, you use some stochastic optimization tools, which is of course fine, but that still has a lot of assumptions and still relies on some models. Or you go into the route of reinforcement learning, whereby you say, okay, there is some uncertainty, I cannot use traditional optimization, and can I design an algorithm which can, with deep learning, it can do some prediction, but even without deep learning, that can solve that problem. And when you go a little bit more distributed by, let's say, multi-agent, let's say multiple base stations trying to optimize the power without a central controller, then you have this intersection between RL and game theory, because the foundations of the optimization problem is really a game, in the sense that you have a series of, let's say, n optimization problems. Their solution is what we call a fixed point equilibrium, which is a Nash equilibrium in the game theoretic sense. And you can use a multi-agent RL or a variant of it. And this is where also things like meta RL comes into play, where you can also use some sort of control to improve, training, to improve the speed of your solution. And finally, I think the workshop itself is dedicated to this topic, which is what we call edge learning or distributed learning. So most classical machine learning algorithms rely on the leftmost paradigm in my figure, where you send data to a cloud, and the cloud does some processing in it. On the rightmost side is the federated learning algorithm, where you send your basically your model parameters, and you try to learn a common distribution. What we think of as a potentially more interesting use case in a wireless context is the one in the middle, which is more like collaborative federated learning, whereby there are multiple users. They could be different, learning similar, but maybe not exactly the same distribution. And they're trying to communicate over the network. And here, I think Petar covered it well. You have two different angles. One angle is, I can use federated learning to improve whatever, D2D communication, let's say, to improve some sort of communication metric. Or the reverse is true. I have a federated learning algorithm or a collaborative learning algorithm running, and the question is, what is the communication metrics needed to make it run well? So I will talk later in the actually talk about the impact of like transmission errors, of delay on these sorts of algorithms. So I think that's kind of a broad view on where I see ML working in wireless. And that's really my last slide.
Thank you, Walid. Thank you. It's extremely interesting. And I don't know if Denise wants to have one slide, although you already mentioned that maybe not. But I would like to give you the chance.
If for the sake of time, you are doing better not to do it, or I can just briefly show, maybe like very quickly go through them. If it's up to you.
Please, you can show that.
Okay, so I mean, I think we are all kind of converging the same type of, like classification of problems and where ML and communications come together. So that's why I'm not going to go into much details. So the first one I had in mind was also basically ML and communications, which is more or less what I talked about. So this is actually, let's say we want to do some machine distributed learning, whatever kind of type of learning we want to do. And somehow, because either the data is distributed or the agents are distributed, the processing is distributed. So now we like it or not, now they have to communicate. And now we have to design the type of communication system that is, for the particular learning application in mind. And of course, then there is the I think very similar to also the previous kind of classifications, is the ML for communications. So I think when you also mentioned that, when people started using ML for communications, some other people, let's say, being skeptical, was more about, this aspect, because, I mean, the first aspect, basically, there's nothing to be skeptical about, because, I mean, if you have to do, like distributed kind of learning, you have to communicate somehow. But, and I can kind of understand why people were skeptical for, ML for communications, because this is, as opposed to, let's say, some of the most kind of popular ML applications where all this kind of most striking results came about. I mean, communication problems, at least the problems that we had in mind, were things that we had very good solutions, right? So we had all these kind of amazing networks, like internet over wireless, so on and so forth. So, I mean, what could kind of machine learning get us, and how could this be even better than it? It is still not clear, actually. So this is, I think, research-wise is very interesting, but we still don't have any of these things actually implemented on kind of designing the communication aspects of the network using these ML tools. But I think, I mean, here basically I put some examples. I'm not going to, of course, like mention these at all, but I think the potential here is, either problems that we didn't actually have solutions, right? So good solutions like communication with feedback, like joint source channel coding. I mean, we kind of went around these type of problems. So we built things that work good enough, but we knew that they are not optimal, and we didn't know how to do things even close to optimal. We didn't even know what the optimal is. So I think for that type of problems, and these are becoming more and more kind of pressing, I think ML has a lot to say. And again, I think already mentioned before, kind of these two aspects which are related to security and privacy. So either using kind of machine learning for secure and private communications. This is again related to the ML for communications, but with the security aspect. And again, typically the problems are very hard, so machine learning can help us. And also kind of, for example, some of these kind of concepts, privacies, that are very difficult to quantify. Or let's say, I mean, we can, for example, define privacy statistically, like I can measure information leakage by the mutual information, but its practical meaning is actually not clear. So we don't know if I leak, I don't know, 3 bits per sample of mutual information. So what does it mean? Is it private? Is it not private? Whereas kind of, we can use this kind of adversarial training, etc., to get, let's say, more data dependent measures. Of course, they're also questionable in other aspects. And then, the coding for secure private ML is the kind of area where, again, tools from coding theory, information theory, communication can play important roles. This kind of relates to also some things I already mentioned in the talk today, but, I didn't touch upon this aspect, but, again, so the whole point is that, these tools we know work for, security, privacy in general, for secure private communications. Now they can also be used for machine learning problems. So that's all I want to say for now.
Thank you, Denis. Then let me somehow try to make a sort of very rough summary that if we look at the research going on here for machine learning and networks, machine learning and wireless, very, very roughly, we can say that we have two categories, and one is how to do machine learning over networks, over some wireless networks. And the other category, research category, is the usage of machine learning for redesign the wireless the networks, and for the optimizations and for the protocols. And it seems that also based on the various use cases that we have seen from Ahmed Eriksson, that there is a clear technological need of having machine learning over networks, machine learning that where data is distributed over devices and so on. And the other category of the usage of machine learning for redesigning protocols and wireless is less obvious, and it's perhaps still many important open questions. Therefore here my question here, at least I would like to hear your opinion from a scientific, from a technical point of view, is it what would be now more intriguing to work with? Is on the first rough category that I mentioned, or on the second?
I could give a quick answer. I think for someone entering the area, the first, which is machine learning over networks, is a bit of an easier, with a bit of less barrier to entry, because you're a comm theorist, right? And then you can just see it as another application running over your network, and you would focus primarily more on the comm challenges. On the other hand, the second area, there are some fundamental ML challenges, and it would require a little bit more knowledge in how ML works and what doesn't work. So I think that's kind of my very brief view.
Do you think, Valid, that it's something that machine learning will really create some breakthrough in fundamentally new protocols? What is your feeling?
So I think that should be our goal in some sense, right? So I mean, we know that applying some of the machine learning solutions has some interesting results, and we've seen that in a lot of works. But we know also there are many limitations, and working on resolving those limitations is important. For example, when we talk about using RL for let's say adaptive network optimization or resource management, we know it works well, but we also know that there are convergence and reliability challenges. Convergence in the sense that some of the RL tools are slow to converge. We all admit that. We have solutions to that, but I think we need fundamentally new results there to make it, let's say, amenable to deployment in wireless. Second is, for example, RL is not reliable. When we talk about applications where you might encounter wireless network states that you haven't seen before, RL can adapt to it, but it takes time. And it depends a lot on the training, and we don't have a lot of data. So we would need some magic there to redesign some of the algorithms or combine techniques even to make things work. So that's why I say that, yes, we would have protocol breakthroughs, but it's not obvious, and it's not gonna be, let's take this deep Q learning, run it on our wireless system, and it's great. Doing that, I mean, we've done that maybe 5 years back and worked well, but now is the time to go beyond that.
It seems to me that in this regard, the application of machine learning over IoT and wireless network is again, it's clear technologically motivated, and we see very tangible use cases. But then this other way, that is the design of the wireless using ML, at the moment it looks quite risky. So we don't know whether it will be actually convenient or not. And so it's an area with more uncertainties in a sense, a research area. What do you think?
Sorry, go ahead.
Yeah, go ahead, please.
Okay. No, I was going to say, actually, I mean, exactly for the reason you mentioned might be actually kind of a motivation to look into, this problem more. Because, I mean, I agree that, of course, the data from IoT, how do you kind of generate machine learning algorithms, this kind of anomaly detection, et cetera, et cetera. So you can do a lot of machine learning on network data, either, data collected from wireless devices or even data about the network itself. But to be honest, actually, in my opinion, in academia, I mean, because actually those applications are, very promising, and actually they might have direct kind of applications, I expect, and I see companies are much more onto those, and it might be a bit difficult actually to compete with them, when there is such kind of commercial potential. So if from my personal perspective, actually, I mean, it's more risky kind of direction. Might be more appropriate for academic research, because that's also kind of more open, things, we can come up with things that are maybe not, so much conventional now, but, hopefully for the future, they might change things.
Yes, it's my own personal opinion that I agree with you that in a sense, to do research on the application of ML over IoT we know that there is research gaps, but also we know what we would expect if we solve those gaps. In the other case, if we instead do research on the usage of ML to radically redesign wireless, we at the moment it's really risky. We don't know what would be the results yet, but nevertheless it's intellectually very stimulating and might make much more sense to do this research in academia, since on the other side, the other kind of research can be well done by companies that would like to build new services and products. But Ahmed, I guess you wanted to add something here.
Yeah. Well, I may add a point here, actually, as Denis mentioned also. Actually, we have huge amount of data that are generated in the physical layer and also network layer of our communication network to handle or basically to enable communication. And this data is somehow hidden from the application point of view. But actually there is a huge potential to exploit this available data, which is in a sense big and huge, and develop models so that enhance and improve different components of a communication link. There would be big potential for in this path as well for the telecom industry, I would say, to improve the efficiency and like the many different performance metrics that we could measure, I would mention that there are two aspects. One is those part of the communication system that we could well design theoretically, like for example channel coding. So we know how to design a good and maybe the best channel code to cope with the situation. But there are some other aspects that we need to rely on the data. For example, the propagation environments, the hardware components that might have some kind of imperfection, and many of those aspects that we do not have very kind of concrete analytical solutions. And we could benefit from this huge amount of data that is generated through the network and train the model and do prediction, classification, and inference, and kind of do data-aided decision within the network to improve the network performance.
But Javed, do you think that if you can reveal that Ericsson believes that maybe in 10 or 15 years from now, radically new wireless protocols will allow us to do something that is much unexpected now? And what could be that?
We would expect that this kind of technologies to be more present in the future air interface as well, and somehow benefit from these technologies. We may not have kind of radical change, so it would be kind of the evolutions of the system that we have, but it would be more AI-friendly networks and systems. So we are going to have AI or network by the AI in the design process to make this learning and training over the network and for the networks consistent to the network design that we are going to have.
Very good. I think Petar, you wanted to hear also comment or.
Yeah. So I have a little bit of, on one hand, cautious look on this design of the protocols, because for many years we have talked about cross-layer design, revisiting the layering and so on. But the layering has not been changed radically, and the reason is that it has not changed radically because this is the way the systems are scaled. So you can find a way that you can do some cross-layer design within certain setup, but that will not scale to different scenarios. That's why the layering as we know it is one of the best way ways to scale the systems, also backward compatibility and so on. So having said that, we also have to go back to see why the protocols we have designed, they are divided into layers. And there are in principle three reasons. One is to simplify the problems because we could not deal with this complexity of design. Second is to modularize them, so basically to enable different providers to provide different modules, like in object-oriented programming. And the third one is architectural scalability, right? So because this can scale, if you come up with a better design of another module, you can design it as long as it respects the interfaces. So the key point in the current layering that we have are fixed interfaces and modularization. So what I'm thinking is that imagine that we remove this requirement, that the interfaces are fixed. Then the machine learning algorithms or AI algorithms would actually work to negotiate different interfaces between two modules or multiple modules, and in this way define the communication protocol on the run. You see, this is one opportunity where over a long run there can be evolution. So we should not think that the protocols have fixed fields, fixed state machine, but this state machine is kind of evolved based on interaction between different AI modules. That is one way, and another way is that we look into what use the low-hanging fruit there is to go back to see which problems have been very difficult in the past to deal with in protocol design, and which ones we have simplified in order to solve them. If we don't need to simplify based on our approach with machine learning, what could we change? Could we change how the ARQ protocols work? Could we change how the TCP works? Because ARQ protocol and TCP are things which you can describe by hand, and machine learning is solving problems which you cannot describe by hand. And so that means that we have to go back maybe to those problems. But I think the most radical change will be if we learn how to make protocols without standardized interfaces.
This is it appears still quite futuristic because as we know, many industries now are working with the usage of the standardization, and they build the chips and all the electronic circuits. So it's then perhaps this could be that in the beyond the 5G, I don't know if it will be 6G or 7G network. So we will need to have, so to say, a slice that is reserved for wireless-based designed and for machine learning that is used to redesign the wireless. So we'll have one slice at least for a transition, and then maybe in 30 years, 20 years from now, ML might have even a more prominent role.
Yeah, but you can, for example, standardize certain control channels and procedures, and based on which they can negotiate another type of protocol. Right? We're doing that at the moment, but what negotiation is doing relatively simple things. For example, choosing adaptive modulation and coding. That's a negotiation. But that again, you can solve it by hand. The question is, what can be negotiated that you cannot solve by hand?
Mm. And also, what would be the big advantage, right, in these new negotiations? What is that we will be able to do that today we are not in the position to do?
Yeah, but keep in mind, as I said, that the protocols have been made to respect certain architecture, in a sense that, for example, they're following the postal service of routing. So let's say if you have a letter to your neighbor, and if you use the postal service, it will take you to the post office and then back to your neighbor, which is totally inefficient, but it's scalable. The question is, how will the protocols in the future figure out what are the local optimizations which without compromising the overall functioning of the protocol?
Yes, this introduces perhaps or somehow allows me to restate what you already mentioned, that there will be a higher degree of autonomy in the future networks, less sort of rigidity.
Indeed.
And I guess also Hamed had mentioned something about this in his roles with these boxes of activities. But there is also another, there is a concept that I wanted to mention that, and is connected now to this research questions, that when I believe in the 1920s or 1910s, in the beginning at least of the previous century, people were doing experimentation to send information over wireless and to improve protocols. And then all of a sudden they discovered that between a transmitter and the receiver that were a few hundred meters far away, and they discovered that when a car was going through, which is somehow big metal object, and there were strange variations in the radio strength and in the received signals. And so this somehow data-based observation then has led to the creation of very efficient radar systems. It might be also here the case that if you try to remodel, to apply machine learning over wireless networks and for the design of wireless networks, something totally unexpected will emerge that could have a groundbreaking effects in our daily life. At least this is one of the things that we can hope. Please, Ahmed, yes.
Yeah, this is an interesting area that you mentioned, Carlo. So we do envision that the networks or the wireless radio networks that we already have as a kind of basic infrastructure that we have widely spread over different countries and different regions. In future, they may not be only used for communication purpose. This radio infrastructure could be used for wider range of applications, for example, for radar application, for localization purpose, for energy transfer, and many different vertical applications. And in this wide range of applications, it is envisioned that they could potentially benefit from the collected data. So we could see that the radio networks would be in place, but not only for the communication, but also for wider range of applications that could potentially benefit from the different type of data that are collected and the models that are trained. So,
yes, a few years ago, I was, I think about 5 years ago, I heard that the base station networks that Ericsson has can be used to do very accurate weather forecasts, just looking at the received signals and the way they are attenuated by the atmosphere. And that so it's a service that is absolutely not communication service, and comes from some sort of data analysis, machine learning from information from the wireless networks. Okay, now we need to finish relatively soon. We have been speaking for almost 1 hour. I think we will have about 5 minutes more, and I have not so far. I have not picked the questions from the audience, and I wanted to give the chance if there is anyone now in the audience that has question, and I have got at least a few technical questions, but some of them we have been already debating. One is this, for example, is how to incorporate knowledge domain into machine learning workflow, and how much it can improve the performance. And is it tough with deep learning? This technical question. Anyone wants to? Again, do you think that there is a way to incorporate a knowledge domain into machine learning workflow?
I may take this question. So So there is potential to using this kind of like transfer learning approaches, have these different models or that are pre-trained in different environments, and these models could be possibly distributed over the networks and where specific users could fine tune the model based on the very limited data that it has. So it's envisioned that this kind of transfer learning together with the pre-trained models in different domains could enable this fine-tune models for various range of applications that could be enabled by the networks in the future.
Thank you, Hamed.
Maybe I can mention something, Carlo. I mean, the thing is that let's go back to this design of protocols and communication schemes. By focusing on a certain part, for example, of the communication system, you're using domain knowledge, because you say, okay, now I want to design a retransmission scheme, so it has to be in some sense following some ARQ protocol, state machines, and so on. And the interesting thing is that domain knowledge can help to speed up this, but it can also be restrictive, because you are not maybe asking the questions, what else I can remove from the domain knowledge that I know and search a larger optimization space, right? For example, instead of having ARQ protocols with a feedback 0 or 1, you can work with protocols that have a richer feedback.
Yes, so that's an important concept to keep in mind, that the design space and the knowledge can be much wider, and it's good to try to look to expected solutions, but also unexpected solutions.
I also want to add to very shortly, because this, I think, is something that comes a lot, you know, so kind of as if there's this kind of dichotomy between, you know, like either we use our models, optimize, you know, this kind of model-based approach, or there's this kind of complete extreme, you know, neural network, whatever base thing, that solution that, you know, we just, you know, put the data and then it learns whatever. But I think, you know, and also, I mean, if I read the question, you know, like this kind of, it mentions that, okay, you know, how do I learn my wireless domain knowledge kind of to use machine learning? I think the main issue is that, you know, in wireless, as we talked, so we already know a lot of stuff, right? So we already know many kind of coding schemes, modulation schemes, etc. So the issue is that, I mean, we can reuse a lot of that information. For example, I mean, just one kind of specific example, but I think it kind of exemplifies this aspect very good. That so we look at this kind of compression problems. So we use, you know, in general, we know that data compression is very difficult, and even, you know, all these years of standardization, whatever, you know, we have this image compression standards, but now people are already doing better kind of compression with neural networks. But in one component there, you know, after you kind of do this kind of feature extraction neural network, at the end you do lossless compression. So now, you know, with lossless compression, we know how to do. We have actually information theoretically optimal kind of, you know, entropy coding schemes. So now there's no point to use a, you know, a neural network to do that. So I think that is kind of this type of places where you put together your domain knowledge, you know how to do certain things, you know how to model certain things, but you know where to kind of also, you know, as Petar mentioned, you know, relax the constraints, and, you know, and you don't do things, you know, like, I don't know, you don't relax the constraint too much, for example, you know, make the power a real number, right? So we know that, you know, like as wireless, you know that the power has to be limited. So I think basically you need to know kind of both aspects and, you know, put these two together.
Absolutely. Very good. At this point, we don't have more time, and unfortunately, I cannot get more questions from the audience. I guess that our speakers will be also happy to answer over email if they get any question. And I really would like to thank everyone of our distinguished speakers to have dedicated their precious time to to this event today. And now the program is that we have a 10 minutes break, and then we'll start at 5:45 with the talk of Walid.
Carlo, I guess that we have already consumed all the break for the panel. So if it's okay with Walid, maybe we can start after just 1 minute or two. Or if you need some more time to rest, we can just give like 10 minutes.
It's up to Walid.
Yep.
I was able to join back. Sorry, I was disconnected. My Wi-Fi router restarted.
Oh, sorry. Yeah, so the question was that we have consumed all the time for this 15 minutes break for the panel discussion. And if you need some time, we can give something like 5 or 10 minutes break. Otherwise, you can just start.
I can start. Again, I'm sorry, I don't